In Cartesian coordinates, we find areas under curves using rectangles. But how do we find the area enclosed by a curve defined by a radius and an angle? Today, we will learn how to calculate areas for polar functions using integration. Instead of using vertical rectangles, polar area relies on summing up tiny circular sectors. As the angle theta changes by an infinitesimal amount, it sweeps out a wedge-shaped region starting from the origin, rather than the x-axis. Recall from geometry that the area of a sector of a circle is 1/2 times the radius squared times the angle in radians. This simple geometric principle is the fundamental building block for our polar integration formula. By summing an infinite number of these tiny sectors from a starting angle alpha to an ending angle beta, we derive the definite integral for polar area. We square the function r and multiply by 1/2 before integrating. Think of the integral as a radar beam sweeping across the plane. As the angle increases, the length of the beam changes based on the function, capturing the exact area between the origin and the curve within the specified boundaries. Before integrating, you must identify the interval of theta. For a full shape, we often integrate from 0 to 2 pi. However, some curves, like roses, might complete their shape in just pi radians. Always check your bounds. Let's find the area of this cardioid. Since it is symmetric and occupies the full rotation, we will set our integral limits from 0 to 2 pi. This will capture the entire interior region of the heart-shaped curve. Using the identity for cosine squared simplifies the expression into terms we can easily integrate. This is a common step in polar area problems, as the formula always involves squaring the radius function. After integrating and evaluating at the boundaries, the sign terms vanish at 0 and 2 pi. We are left with 6 pi. This represents the total square units contained within the cardioid boundary. Now consider a rose curve. To find the area of just one petal, we must find the angles where the radius returns to the origin. For this function, one petal is traced from negative pi over 4 to positive pi over 4. We can use symmetry to simplify our work. By integrating from 0 to pi over 4 and doubling the result, we calculate the same area with easier boundary values. Symmetry is a powerful tool in polar calculus. Applying the power reduction identity again, we integrate the expression. The result for one petal is pi over 8. If we wanted the total area of all 4 petals, we would simply multiply this result by 4. What if we need the area between 2 polar curves? Similar to Cartesian area between curves, we subtract the inner area from the outer area. The formula becomes 1/2 the integral of the outer radius squared minus the inner radius squared. The most critical step here is finding the intersection points. By setting the two equations equal to each other, we solve for theta to determine our limits of integration for the shared or excluded regions. Be careful! The most common mistakes are forgetting to square the radius or omitting the 1/2 constant. Always sketch the graph first to ensure your limits of integration match the region you intend to calculate. To summarize, polar area is calculated by integrating 1/2 r squared with respect to theta. Use symmetry when possible, find your intersection points carefully, and keep your double angle identities handy for those squared trigonometric terms. Quick check, which integral setup correctly represents the area of the circle r equals 3 sine theta from 0 to pi. If you chose B, you correctly included both the 1/2 factor and the squared radius. Mastering polar area opens the door to understanding complex motion and natural forms. Practice with different r functions to build your intuition. Thank you for watching this lesson, generated by Vision Solve AI.